That microphone.
Yes.
This one? Either of them.
Wei, can you hear us?
Yeah, I can hear
Can you
you.
say something so that we can hear you?
Can you hear me? Can you hear me? Yeah, let me. Can you hear me now?
Someone's busy working in the booth.
Can you hear me now?
Into the room. Okay. Is there a
Peter,
quick fix to that or a simple?
online people can hear me, so
It's coming through your laptop, but not into the.
Try to get. Can you talk again, Wei?
can you hear me now?
Stretching exercise.
A little yoga. Are you suggesting, Shakti?
Wait, can you speak one more time?
Yeah, test.
Sorry, we're having trouble hearing you in the auditorium. Give me one moment, please.
Yeah. Mhm.
How many of you will also be here through the spring? Most of you, right? Okay, good. We've been already planning the spring program on learning and games. And everything you've been talking about is highly relevant there. In the game setting, robustness is key. Non-convexity issues happen all over the place. All kinds of dynamical systems issues. And so it's great to see applications to neural nets. That's kind of great prediction. It's a thing, but prediction and games going together, it's really, I think, much richer. Because we can't trust the data. There may be an adversary who wants to mess up the auction. When you're doing it classically, you just assume those things away, more or less. But if you have data coming in and they're coming from real people, you can't assume them away anymore. So the real world problem demand should be robust, even much more so than neural nets. Because there's going to be an adversary almost by definition. So I'm excited how that program is going to go. I think some real new ideas will come out of that. And of course, the classical literature was very convex.
Can you try again?
Von Neumann, duality, et cetera, et cetera. And the modern problems are not convex anymore. And Nika Haktalav in our teaching class from scratch, really.
Sorry, one more time.
Example, something I'll be
Can you hear me?
something called incentivized exploration, which is a little thing. There's kind of like Alex Slifkin's works on it, and I think Yisham Mansour worked a bit on it. It's where a whole group of us are trying to both explore and exploit a set of options. If we're all by ourselves, it'd be a bandit problem. I just explore a little bit and exploit a lot. But if I can watch the rest of you too, I hope you will also explore. But if you're watching me, you're probably not going to want to explore. You're going to free run. All right. So is there a way to incentivize each of us? So you can, and it's a clever way to do it. There's a
Yeah, Martina, if you want to try talking, maybe we can hear
Hi,
you.
yeah, so we can hear Wei on Zoom without a problem.
I know. Yeah, it's just coming through the auditorium. It's not coming in.
So it's kind of a slippery way that you can get a central person to have each of the group do a little exploration. The whole group profits from that. So a whole bunch of interesting problems come up there. That's next week's lecture. The central person gets to know all about the data of all the others, and we don't. Need to, absolutely, that's right. The output can be a multi-party computation, but also kind of effectively what you have to do is solve that. And you can get real results, and clearly they're just kind of limited right now. Just getting started. How are we doing there? Okay, so it's a local problem here in the room. There's not just a button to press somewhere. If you were to bring yours up here and connect it with that.
It wouldn't have to be mine.
Yeah, I hope he's. Hello, do you hear me? Wei Hu?
Yeah, I can hear you. Can you hear me?
Did you hear him?
Do you hear me?
Yes, I can hear you. Can you hear me?
No. I've also lost control of my ability to
Yeah, that should
turn that on because I guess you've hooked me up, right?
Right. So where's your? Let's make sure these are up. Let's try that again.
Hello?
Let's try display port. Wait, can you hear? Can you talk now?
Yeah. Hello? Hello?
See, let's try a different.
So you guys can't hear me. Philippe Rigolet, do you hear me? Philippe hears me.
I can hear you.
I'm on Zoom. Wei Hu, don't you hear me?
I can hear you.
He's saying he can hear you, but it's not coming through.
Wei Hu, do you hear me? Say yes or no. Okay, Wei Hu hears me, but his is not coming through.
This is not coming into here. It's coming through there.
If you unplug and just put the volume up, can we just hear it if we speak?
Unfortunately, because he's put this thing
Yeah,
in
but if you
here.
unplug it.
Maybe just unplug.
leave
Okay,
your-
you're right.
Yeah, maybe.
Let's try that. Okay, let me just put the volume up. Good point.
Yeah.
All right.
Where's
There's echo.
Okay, try.
Hello.
Of all the microphones? Can you mute the microphone?
Hello. Can you hear me?
Okay, yeah. Okay, do you hear us now, Wei?
Yes. Can you hear
Okay,
me?
I think he got the feedback loop closed. Okay, so you can give your talk. We're gonna hold a microphone up in front of my computer, which is about the best we got here, but I think that'll work.
Okay. So do you hear me okay? Is the sound?
Yeah, I hear you okay. Do people hear you in the room? Okay, you can go. Go.
Okay. Good. Sorry that I cannot come to the campus today, but I am physically in Berkeley. So today I'm going to talk about implicit regularization in deep learning. So let me just start by briefly reviewing the pipeline of deep learning. So usually we first need to have a data set. So for example, ImageNet is one of the most popular. And then we need to design a model. And in the context of deep learning, the model is usually in the form of a deep neural network. And there are usually many parameters in the model. And we want to find a configuration of these parameters such that the model can perform well on the data population. And the way to find such parameters is to try to minimize some loss function, some training loss function, which basically measures how well the model performs on the training data set. And in practice, the loss is usually minimized by the gradient descent algorithm or some variants of the gradient descent algorithm. And this pipeline has achieved tremendous success in practice, which is very mysterious from a theoretical perspective. And one of the biggest mysteries in the theory of deep learning is the so-called generalization mystery. That is, over-parameterized neural networks can generalize well, meaning that they not only can fit the training samples, but also perform well on unseen test samples. So let me use a simple example to illustrate this. Let's say that this is our training data set with images of cats and dogs. And when we train a neural net to classify these data sets, the neural net could learn this blue boundary, for example. But because the model is usually highly over-parameterized, it is also capable of representing very complicated functions. For example, this red boundary, which looks very different from the blue one. But these two solutions perform equally well on the training data set. So they both have zero training error, but they may perform very differently on new test samples because these two are very different functions. So that means even if we successfully solve the optimization problem and get small training error, that doesn't imply we will have generalization. We will have small test error because in principle, we don't know whether we found the blue solution or the red solution if we just look at the training error. But in practice, just by minimizing the training loss using gradient descent-like algorithms, we can somehow often find solutions that generalize well to test samples. And this is the mystery that's not well understood. And what is believed to be an explanation of this behavior is that there's an implicit regularization effect from the optimization algorithms we use. So the main proposal is that the optimization algorithms such as gradient descent or stochastic gradient descent prefers low complexity solutions. So even if the whole model space is very complex, gradient descent will only find certain low complexity solutions for some reason. And that, if that's true, that would imply good generalization performance. So I'm going to present two simple deep learning examples where we are able to mathematically characterize the implicit regularization going on there. So the first one is for linear networks, and the second is for nonlinear networks. So let me go into the first example. So for this example, we will consider this classical problem of matrix completion. So the goal of matrix completion is to recover a low rank matrix given only a subset of its entries. And this is a well-studied problem in machine learning and statistics. And the typical application is in recommendation systems. So think about predicting user ratings, but given only a subset of the ratings. So today, for simplicity, we will just assume that this ground truth matrix, which I call M, is a square matrix. So it's a D by D matrix, and it has low rank. So how to solve this problem? So first, we can easily write down a naive training loss, which looks like this. So we try to find a matrix W, which is our model that minimizes this training loss over the observed entries. And of course, many optima exist for this problem because we can just assign any values to the unobserved entries. So there's no hope of recovering the true matrix M using this naive approach. But that's simply because we haven't used the assumption that the matrix should be low rank. So we may want to add some explicit regularization to encourage low rank. And the classical approach is to add a nuclear norm regularization like this. So recall that nuclear norm is the sum of all the singular values of a matrix, which can be viewed as a convex relaxation of the rank. But what we are considering today is a different and a counterintuitive approach, which I call a deep learning approach. So what we do here is to try to find this matrix M as a product of multiple matrices. And in the language of deep learning, this can be viewed as a deep linear network because it's parameterized as a product of L matrices W1 through WL, which is a composition of L layers of linear transformations. So here's the objective function corresponding to this approach. And so it's a function of these L matrices W1 through WL. And notice that here I'm requiring all these matrices to be size D by D. So by doing this, we are not imposing any constraint on the rank of the matrix. And actually, it's very easy to see that this problem is exactly the same as the problem in this naive method, because we can still express all the D by D matrices using the product of multiple D by D matrices. So it seems that doing this reparameterization doesn't make much sense, and we wouldn't expect this to be useful at all. But the surprise is that empirically, if we just minimize this new objective using gradient descent with initialization close to 0, we can almost always recover the ground truth matrix M accurately. And this is surprising because we are not explicitly asking for a low rank solution in the objective. So the only possibility is that the optimization algorithm we use, which is gradient descent in this case, has an implicit regularization that somehow can help us find the low rank ground truth matrix. And this implicit regularization effect, we can understand it by analyzing the dynamics of the gradient descent algorithm in this problem. And an important step in the analysis is to derive the dynamics of the singular values of the solution matrix, which is this equation. And from this equation, we can see that the depth, the number of layers, L, affects this dynamics via this blue factor. And we can interpret it as inducing a rich get richer phenomenon among different singular values, which encourages low rank because different singular values will grow at very different rates according to this equation. And we can verify this intuition by plotting the evolution of all the singular values during the course of gradient descent. Okay, so basically for this problem, we had a very nice mental picture of how the gradient descent algorithm prefers low complexity solutions. And the appropriate notion of complexity here is the rank of the solution matrix. And we can divide the space of all the solutions according to their rank. And our ground truth matrix might be here, which is a low rank global minimum of the loss function. But there are also many other global minima which have higher rank, and they all have 0 training loss. So what happens when we run gradient descent starting close to 0 is that it will first search over the rank 1 spaces, and then the rank 2, rank 3, and eventually it will settle down at a low rank minimum. So it will never reach these higher rank spaces, so it won't go to all those non-generalizable minima. And this is done implicitly by running gradient descent. So we can view this dynamic picture as indicating a more general statement that maybe neural network learns functions of increasing complexity during training. And the notion of the complexity in this example was the rank of the matrix. And this general hypothesis is to believe to be perhaps true in some sense, but in general, we still don't know what is the right way to characterize the complexity of neural networks. And especially in nonlinear deep neural networks, this becomes much more challenging than linear networks. And next, I'm gonna very briefly talk about another interesting theoretical result along the lines of this general hypothesis. And in particular, we will show that in some natural settings, a nonlinear network trained by gradient descent only learns a linear function first before it starts to learn anything else. And so the formal result is for a standard 2-layer neural network trained by gradient descent. So the network looks like this. So it has 2 layers and there's nonlinearity in the hidden layer of the network. And we also consider a hypothetical process, which is a linear model also trained by gradient descent. So it's just a simple linear model on the input X. So the beta 1 and beta 2 here are the parameters in this linear model. And what we prove is that these 2 processes can be coupled. And specifically, in the early time of running gradient descent, the neural network and the linear model compute almost the same function for input X coming from the underlying data distribution. So that means although the neural network has nonlinear capacity, when we are running gradient descent, it will implicitly bias the neural network towards a simple linear function at the beginning of training. So this is also a very interesting implicit regularization effect. So here are some experiments to verify this result. So basically, these plots are showing that the neural network and the hypothetical linear model basically behave the same in the early time of gradient descent, which verifies this theorem. Okay, so to conclude, I argued that the implicit regularization effect from the optimization algorithms is key to understanding the generalization behavior in modern deep learning. And I presented 2 case studies where we are able to show that show exactly how neural network learns functions of increasing complexity during the course of gradient descent. And these examples also show that perhaps analyzing the dynamics of the learning procedure may be important to understand, or even just to describe the implicit regularization effect in deep learning. Okay, that's the end of my talk. And feel free to get in touch if you are interested in chatting about deep learning. Thanks.
We'll move to Manolis now. So I just sent us in a chat. Manolis, do you hear me?
Yep, I can hear you. Can you hear me?
Yes,